Hello everyone, my name is Samuel Contos and my project partner's name is John Andrus. For the project in heat transfer this semester, we attempted to tackle the question of the viability of an in-ground heat pump in southeastern Idaho. And for those of you who don't know, a heat pump is essentially a refrigerator, or often a refrigerator and heating unit that's run backwards. You run backwards for the heating, and then in the summer you can run forwards for the cooling. And many of these are above ground and use the ambient air for their heat transfer. As a fundamental aspect of heat exchangers, we know that they benefit significantly from a larger temperature difference between the reservoirs and the ambient air. So a heat pump attempts to dump air from the house into the ambient air, or dump heat from the house into the ambient air in order to cool the house, or pull heat from the ambient air into the house in the wintertime to warm it up. In the winter, though, the air outside is cold and there's not much heat in it, and in the summer the air is hot and it's hard to put more heat into it. This is where the benefits of going in-ground come, because in-ground the temperature is much more consistent and in the middle with regards to the fluctuations of ambient air temperature, which means in the winter it's easier to put heat into the ground or pull heat from the ground, and in the summer it's easier to put heat into the ground and out of the house. This can result in increased efficiencies for heat pump and refrigerator systems, and thereby saving the homeowner significantly on cost. There is, however, an upfront cost associated with an in-ground heat pump. As we mentioned, ground temperature fluctuates much less than air temperatures. You can see here on the left, at different depths, the fluctuation in ground temperature in degrees Fahrenheit throughout the days of the year. Air temperature can be approximated by the surface ground temperature, and at a depth of around 12 feet, the ground temperature, as you can see there, that smallest curve, fluctuates very little, and that's where you get your most benefit for an in-ground heat pump system. You use this relatively consistent temperature to both pull heat from that temperature into the house when it's really cold outside in the wintertime, and to put heat into it when it's really hot outside in the summertime. And then on the right you can see that different soils behave a little bit differently, but generally as you get closer to the surface the temperature will fluctuate a greater amount, whereas at a certain depth it almost fluctuates or it almost ceases fluctuating entirely. To achieve the needed heating capacity for an in-ground heat pump system, a very large length of pipe needs to be buried. We calculated this length of pipe for a couple different scenarios to get a feel for our model and the accuracy of it, but essentially we had the length of pipe in this equation here is equal to the Q, or the heat transfer, times H, the convection heat transfer coefficient, pi diameter over the difference in temperature between the fluid, the refrigerant that was in phase change, so constant, and the ground temperature that we were working at. This provided our difference in temperature, and then with m dot times the latent heat of vaporization and condensation, we were able to calculate our Q, and then with this calculate the length of pipe. This, we didn't put any particular numbers in here because we used a few to get a good grip for how well it was working, but this varies a lot with how much fluid you're pushing through, and especially with how large your temperature difference is. We found that at depths where the temperature difference was within 10 degrees, enormous amounts of pipe would be needed, but as we dropped the pressure of the refrigerant and thereby increase that temperature difference, we could cut down those lengths of pipe by entire orders of magnitude. So it turned out that the temperature difference made the biggest difference in the amount of pipe that you need to bury, which in our case we gained a better temperature difference with a lower pressure of the refrigerant. We also wanted to consider how the ground temperature behaves over time while we're pumping so much heat into it and pulling so much heat out of it over extended periods of time through the winter and summer months. We calculated the change in temperature over time with equation 5.57 in the 5th edition textbook for this class, Fundamentals of Heat and Mass Transfer. You can see that equation on the left here where time in days equals x, which is the distance from the pipe or the object in the ground, over 2 times the inverse earth function of Tx, which is the temperature of interest at point x, minus Ts, which is the surface temperature of the heated or cooling or cold object in the ground, over T initial, which is your initial temperature at x, minus Ts again, all over alpha, which is the thermal diffusivity of the soil. And then on the right, you can see our result here with the temperature change at 1 meter above the heat exchanger pipe. We put the heat exchanger pipe at 12 feet deep, approximately 3.5 meters. And the temperature change there, over the course of 100 days, the temperature only dropped from 5 to about 1.5 degrees Celsius. So we felt like that was reasonable and left us in a position where we could confidently say that having the heat pump, the in-ground heat exchanger for the heat pump, did not significantly affect our ground temperature over time. We felt that the ground would recover over the summer months from the winter heat exchange and vice versa. In conclusion, the upfront cost of an in-ground heat exchanger system can be significant, but in the long run, with much better heat exchange rates and heat transfer rates, the consumer or the homeowner would be able to pay off that investment in the long term. The in-ground heat pump system is much more efficient and would require less energy input and would not negatively affect long-term ground temperature.